So, hello everyone. So, welcome to lecture 54. So, we are actually going to continue upon what we were doing in the previous class, where we briefly introduced the idea of spectroscopy, that is to look at properties over frequency scale, right. And then we said one spectroscopy technique cannot address all the different frequency scales that we have, which starts from something like 0 hertz all the way up to 10 power 19 hertz, which are X-ray frequencies, right. So, you should split this up into different sort of frequency regimes and then understand the dynamics of your properties at different frequency regimes through appropriate techniques, right. So, one of the properties that we were looking at is epsilon r or refractive index, right. So, these are related. We said something like NR, right. So, how are they related, right. So, from Maxwell's equations will just be square root of epsilon r mu r, where mu r is the magnetic permeability, and for non-magnetic materials NR is just square root of epsilon r, right. So, that is the relation, and so whether I talk about epsilon r or NR, I am sort of saying related things, okay. So there we are actually looking at the electron dynamics, the electromagnetic, so the electrons, the dynamics of electrons, how they are oscillating with respect to the applied input, and applied input we are trying to look at all these inputs, right. So, from 0 hertz to 10 power 19 hertz as some form of an electromagnetic wave, okay. So, and then we said, okay, so let us start with what is called impedance spectroscopy, right. So where we looked at this quantum mechanical picture, where if I have an electron that is excited to a virtual state, if I supply enough energy to the electron such that it is excited to some sort of a virtual state, there is no real state there, it is just virtual state, then this system cannot absorb any energy, or this system cannot dissipate the input energy, right. So, those processes are called scattering processes in a quantum mechanical sense, and in a quantum mechanical sense, if I have an electron, right, so that upon application of some energy, right, so gets excited to a real state, then those processes are dissipative processes, or there is some absorption, right. Now, so what do I get, so what is impedance spectroscopy? So, we sort of studied what are called small signal measurements. We did the small signal measurements, right, where the input, the small signal input, right. So, I do not worry about the DC input, but the small signal input is at some frequency omega, and this omega is typically so it can be as low to as high, right. So, let us give it a range 0.1 hertz to about 1 megahertz, right. So, these are the typical lab frequencies. If you take what is called an LCR meter and then measure, do small signal measurements to get the idea of capacitances and the corresponding conductances, right. So, the typical frequencies at which you operate these small signals are 0.1 hertz to 1 megahertz, okay. So, this is the range where we do not need to worry too much about the so how I am shielding the probes, etc. The measurements need to be still accurate, right. So, you need to worry about how the electrical signals in the room, the line frequencies, etc. interfere with your probes, right. So, that you are using to measure, you need to shield them well enough, but so these are doable in a lab, right. So, in my lab, for example, these are doable experiments. So, we do these sort of experiments, right. So, what you get then is you get capacitance, or you get the real part of dielectric constant, right. So, epsilon r as a function of omega, and you also get conductance, or you get the imaginary part of epsilon as a function of omega, right. And so at a particular omega rather, right. And if I want it as a function of omega, I scan the frequencies and I measure capacitance and conductance as a function of frequency, right. So, this sort of a measurement I can do, right. So, these are nothing but the small signal measurements to get this information, right. So, up to about 1 megahertz or even 10 megahertz, if I push my probes properly, I can go and attempt these so let me just write 10, right. So, in a very good lab with everything is well shielded, etc., I can go up to probably 10 megahertz, right. So, to measure the capacitances and conductances. Now, let us look at what 10 megahertz is, right. So, 10 megahertz in energy scale, right. So, E equal to h nu, and h equal to 10 megahertz, nu is 10 megahertz. So, the E will turn out to be something like 10 power minus so you can do the calculation of what this is going to be, but this is going to be about 10 power minus 7 eV or less than that, right. So, for less than 10 megahertz I have energy which is less than 10 power minus 7 eV, or in other words that is 10 power minus 4 milli electron volts, okay. Or I am looking at electronic transitions here. So, that means I am looking at electronic transitions either to virtual states or to real states, right, of the order of something like 1 nano electron volt to about so less than 100 nano electron volts, let us put it that way, right. So, it can be very small, but so the maximum electronic transition range I am looking at are 100 nano electron volts. Now, what is room temperature, so let's just keep an eye of what kT is. kT is about 25 milli electron volts, right. So, these are very small scale oscillations, right. So, sorry, very small scale energy transitions, right. So, less than even what kT does, okay. So, essentially so I said the experiment if I am doing this at 0 Kelvin I am getting rid of the thermal oscillations, let us say at 0 Kelvin so if I am going to measure, this is my conduction band, this is my valence band, right. Okay, so right. So, this is my Fermi level EF of an electron that I am going to I want to inject, right, this electron or I am just going to excite the already existing electron. So, at 0 Kelvin the valence band is completely filled, the conduction band is completely empty. So, I need to excite this from the edge of the valence band, this is valence band edge, EV is the edge of the valence band. I need to excite an electron from the edge of the electron excitation in the valence band. Needs to be about 100 nano electron volts. So, but there are no states so at 0 Kelvin there are no states at about 100 nano electron volts, right. So, as a result so since there are no states, no existing states at about 100 nano electron volts, what I end up doing is I end up exciting to virtual states. So, these all are virtual states, okay. So, these all tend to be virtual states. I am just going to dot them, virtual states that exist so 10 megahertz means it is about 100 nano electron volts. So, this is the energy scale of operation where I excite these electrons to these virtual states and then they spend almost no time there, they come back, they de-excite, and this excitation de-excitation process is what I am measuring as capacitance, right. So, the capacitance tells me about this excitation and de-excitation process, right, or how much energy am I storing, right. So, all these are related to each other, okay. However, so if I want to measure resistance, right. So, I am looking at so let me do the resistance measurement at some finite temperature, because at 0 Kelvin the resistance is infinity, right. So, for this semiconductor, right. So, at finite temperature I will have already some thermal excitation of carriers into the conduction band, right. Since there are already carriers in the conduction band supplying them an additional energy of about 100 nano electron volts, right. So, to these carriers there are so many states here, like these are all real states, right. So, then my spectroscopic excitation, right. So, allows the conduction electrons to get excited to real states. or an injected electron. So, this is actually an injected electron. The injected electron should actually go in and sit in excited states, right. So, these excited states are about 100 nano electron volts above the real states, that is okay, right. So, my incident electron beam, sorry, my incident radiation, my incident electrical signal can give me that sort of energy, which is about 100 nano electron volts per electron. Okay. So, it can go sit in the real state, then it can get transported and so on and so forth, right. So, it gets transported spatially, and then I have a current that is generated. Okay. So, that current tells me what the resistance is and what is the dissipative property, right. So, but in general this dissipation is possible because I am able to access these real states, right. So, the electrons are able to access the real states. If there are no real states, the electron would not transport, right. So, there is going to be no current, right. So, there is just going to be some sort of an oscillatory or displacement current, but there is not going to be any conductive current. Okay. So, so that is the crux of impedance spectroscopy. Okay. Now, impedance spectroscopy ideally, so any sort of electrical measurement that you do, right. So, even people do what are called gigahertz measurements, right. So, all the way up to so 0 hertz all the way up to something like 100 gigahertz, right. So, this sort of frequency spectrum you can just apply probes, not just, I think it is the higher the frequency, the more complicated the measurements are going to be, but you can apply probes and then measure them electrically. So, the signal input electrical signal can be given through electronic equipment. That means I have a signal generator, I have probes which are actually physically touching the electrodes, which touch the electrodes, right. So, I have these sort of probes, I have my electrodes, 2 electrodes, right. So, I have a ground probe. So, this is a source, this is ground, right. So, and then I can apply a signal generator, right. So, between these two, and I can measure, so this is what is in between is my device under test, right. So, I can measure the capacitance and resistance of this device under test. This is device under test. Okay. Still this is called spectroscopy because I am getting a frequency related information, and I am getting that of both the imaginary part of dielectric constant as well as real part of dielectric constant. So, both these things I can measure through what is called impedance spectroscopy, and the electronic processes that this is probing are so near valence band and near conduction band, and these are about 100 nano electron volts electronic processes, right. So, what does impedance spectroscopy probe? About 100 nano electron volts of electronic processes, right. And these processes are so excitation and then de-excitation, excitation into either a real state or a virtual state, and de-excitation back to the ground state, right. So, those are the processes that I am interested in. Okay. So, this is so this is a new way of looking the transport measurements. Transport measurements are also spectroscopic in nature, right. So, that means you are actually exciting the electrons that are present in the system by about 100 nano electron volts, and then a property emerges out of that, and that property that is coming out of the dynamics of these electrons is capacitance or is resistance, right. So, there is a dissipative and there is a conservative property, both of them come out of such such dynamics, and these dynamics you are triggering them with input small signal AC voltage, and so you are measuring it, right. So, you are measuring it electrically. So, everything is done electrically. Okay. So, now I want to actually show you that so up to like I said up to 1 megahertz even I can do these measurements in my lab, right. So, but beyond 1 megahertz or so if I am doing something like gigahertz measurements, these are easier to do, right. So, so about 100 gigahertz, right. So, this is what is called RF measurements or radio frequency measurements, right. Radio frequency or so if I am actually going up to 100 gigahertz or sub terahertz, these are called what are called millimeter wave electronics. Now millimeter, because at about 100 gigahertz or terahertz the wavelength of your electrical signal, or there is an electromagnetic wave, right. So, I have an electrical signal, the electric field is varying with time, right, at terahertz frequency or at 100 gigahertz frequency, and so that means that there is an electromagnetic wave here, right, or electromagnetic signal, right, and the wavelength of this electromagnetic signal is about millimeters, right. So, in these frequencies some special attention needs to be made to the way that you are actually measuring, so to your measurement protocols are different, and not every lab in this world can do these sort of measurements, right. So, these are specific measurements that need to be done, only you have to develop some sort of expertise to do these sort of measurements. Okay. So, I am going to show you. You can still do it electrically, but then you have to be very careful in and what care are you going to take, right. So, essentially if you have probes, right. So, these probes are always so the probes are also, they act as inductors, right. So, they can gather some electromagnetic radiation from outside, or so they can act as inductors, and they can add to some additional elements that are not present in your material, right. So, you can have contact issues, you can have probe issues and other things, right. So, all these things exaggerate as you keep on going to higher and higher frequencies when you are actually measuring, right. So, now here I am actually showing you one of these probes that we have in at micro nano characterization facility in SENSE. SENSE is Center for Nanoscience and Engineering in IISc, right. So, this is an RF probe, right. So, this is to do RF measurements, which means gigahertz and more than gigahertz, right. So, if you have to measure capacitances and resistance, you use these sort of probes, right. Now, you see that one probe itself, right. So, that is somewhere there is a probe tip, and you are going to connect it to your sample, right. So, this is the optical microscope to see your devices, right. Just one probe tip is this huge, this is one probe tip. Okay, so what is, and this is the second probe tip. Whereas in regular measurements I just use a small tungsten probe, right. So, which is shielded with some what is called BNC cables or triaxial cables and so on. So, the cables sort of shield these probes against external interference of electromagnetic waves, but here you need this entire dabba to actually shield your one probe, right. And so this is how you actually shield any sort of radiation that comes and interferes with your measurement, right. So, this is the so I am not going into details of this, but all this huge chunk of the peripheral is really needed to shield any sort of electromagnetic interference of that your probe can see and pick up from the surroundings, right, and give you artifacts in your measurement, right. So, you have to shield all the other external nonsense to be able to actually measure what is coming from your device, right. So, it's a that is why so you need the equipment, the building of the equipment, the building of the shielding things, etc. So, this is where the complexity lies in doing these millimeter wave measurements and RF measurements, right. So, millimeter is much more complex than RF measurements, right. So, only a handful of groups in the world do this millimeter wave measurements, right. So, so there is some complexity in doing these measurements, right. So, up to 10 megahertz even I can do, but beyond that you really need to develop some sort of expertise to do that, right. So, and in SENSE so we have actually few faculty that are experts in doing these sort of measurements, right. So, and on various material systems. Okay. All right. So, that is a small detour just to show you that it is not just about knowing how to do the measurement, but also it is not just about the theory of doing measurements, but when you actually go and really do these measurements, right. So, then you realize that so physics is okay, but there is more than physics, right. So, how do I really do the measurement without the probe interfering with the external electromagnetics, etc. How do I shield these probes? All these things come into play, right. So, all these things need to be thought out quite well. Okay. All right. So, that is about impedance spectroscopy, right. So, the sort of so all the way from 0 hertz to so let's give it a range of up to 10 to 100 gigahertz. All these processes I can measure using impedance spectroscopy, right. So, all the capacitances, the variation of capacitance with frequency, the variation of resistance with frequency, right. So, if I do these sort of measurements and I do them electrically, so all these things go under the umbrella of impedance spectroscopy. So, electronically I am actually still near the valence band or conduction band, and I am looking at processes that happen near the valence band and conduction band, right. So, this 100 nano electron volt processes that happen near the valence band or conduction band. Now, let us increase the energy scale, right. So, so this is 0 hertz, this is about 100 gigahertz. I can do all these things electronically. But if I have to measure a dielectric constant at optical frequencies, right. So, what are optical frequencies? Optical frequencies are somewhere here, right. So, that is about 10 power 15 hertz, right. So, I cannot really create a probe, an electronic probe that can apply, I cannot really give an electrical signal at 10 power 15 hertz is not possible, right. Rather I will shine light, because light by itself is an electromagnetic radiation with frequency of 10 power 15 hertz, right. So, starting from about so something like a few 5 terahertz or something like that and above, right. So, here I use light or an electromagnetic wave of that frequency as a probe. Here I use electrical probes, right. So, these are for lack of a better word, if I am saying I do electronic measurements. So, in these frequencies I do electronic measurements, in this frequency I do optical measurements, right. So, I have to go to optics from electronics, right. So, right about 100 gigahertz, so I cannot do electronic measurements anymore, I go towards optics, okay. Now, there is a gap here, and this gap so people are trying to fill it from both ends. So, this gap here is what is called the Terra-Hertz gap, where to come towards it electronically is challenging engineering wise, and to come towards it optically is also challenging, because now I need to create optical sources at terahertz, right. So, at these sort of terahertz, okay. So, this is an area of research that people are trying to fill this small gap, where so really I cannot really do electronic measurements, or I cannot do optical measurements to understand the phenomena that are happening in this gap, okay. Now, having said that, now let us so we went up to 100 nano electron volts, right. So, let's up the ante, right. So, let us go to next so about milli electron volt time scales, right. So, 100 nano electron volts, but if I go towards gigahertz, right. So, this is 10 megahertz, but if I go to 10 gigahertz I am at times 1000. So, 100 times 1000 is 100 micro electron volts, right. So, okay, so let us say electronic measurements I will stop at 100 micro electron volts, that is still 0.1 milli electron volt, okay. So, this is the energy energy processes, the electron excitation energy processes that I see using impedance spectroscopy, okay. Now, let us up the ante. Now, I need to measure from in order of 1 milli electron volts and greater than 1 milli electron volt and 100 milli electron volts, right. So, there are several spectroscopic techniques to do that. So, one is called Terra-Hertz spectroscopy. For example, right. So, if I look at epsilon r versus frequency, the epsilon r has an ionic resonance, right. So, resonance ionic polarizabilities resonate at certain frequency, right. So, this frequency f naught, that is in terahertz, right, and the way to probe it is by doing what is called Terra-Hertz spectroscopy. So I do Terra-Hertz spectroscopy to actually measure these sort of resonance and anti-resonance peaks of epsilon r, right, or so in some sense ionic polarizabilities are nothing but the bond polarizabilities, right. So, the bonds are extending and coming back and so on and so forth, and bond polarizabilities so are captured by what are called phonons, right. So, if I am doing what is called second quantization, let us not worry too much about it, but these are nothing but lattice vibrations, bond polarizabilities, right. So, they are there is some dynamics of bond polarizabilities, and these are nothing but lattice vibrations, and lattice vibrations quantum mechanically can be thought of as particles which are phonons, right. So, just like I can think of electromagnetic radiation as photons, I can think of these lattice vibrations and sound waves inside my material as phonons, right. So, essentially I start digging into phonon frequencies, right. So, using these techniques of 1 milli electron volts to 100 milli electron volts. The other technique is what is called Brillouin spectroscopy. So, these are sound wave based, right. So, Terra-Hertz spectroscopy, I give a Terra-Hertz wave, right. So, a Terra-Hertz optical wave, and then I measure at Terra-Hertz frequency, and I measure the output at Terra-Hertz frequency, and I get an idea of what the epsilon r is in that frequency. Okay. So, now Brillouin spectroscopy also can be also is used to measure phonons which are whose dynamics are 1 milli electron volts to about 50 milli electron volts or something like that. So, these are what are used to discuss what are called acoustic phonons, the low energy phonons. Okay. So, this is a sound based technique. Okay. But then I have ISC is famous for hosting, or so Professor C.V. Raman, who got a Nobel Prize, right. So, Raman spectroscopy, right. So, this actually looks at energy scales which are from 10 milli electron volts to about 100 milli electron volts, right. So, this looks at what are called optical phonons in a material. Now, how does Raman spectroscopy work? So, I shine a photon, right. I shine a photon at say h nu. So, this is 532 nanometers, which is visible light, right, and then I detect another photon which has a frequency of h nu minus or h nu 1, right, h nu naught, and then I detect a photon of another frequency h nu 1, right. Now, so which means that there is a shift, right. So, if I look at energy versus frequency, right. So, the incident energy is here, right. So, this is nu naught, whereas the detected energy is somewhere here. This is called a Stokes shifted, so this is nu measured or nu 1. Okay. So, this is incident and this is detected, right. So, then what am I saying? I am saying that there is some process in the material that has absorbed nu naught minus nu 1 amount of energy, right, h nu naught minus nu 1 amount of energy. Okay. So, now so what are these energies typically? These energies are in 10 to 100 milli electron volts, and what is that thing in your material that has absorbed such an energy? These are typically phonons or lattice vibrations. Right. Now, again, if I look at the electronic band structure, right. So, this is the conduction band, this is the valence band. Valence band has all sorts of bonding electrons, right. Your outermost electrons, right. So, you can think of a molecule which is bonded using s orbitals or p orbitals, whatever it is, but the outermost electrons that are used to bond between two atoms, those are the energies that I am describing in the valence band, right. So, conduction band is more sort of free electrons, but valence band has bonding electrons, right. Then I am looking at the excitations of lattice, meaning these bonding electrons, the bonds, right, by about 10 MeV, right. So, again it is the same process, but now I am digging deeper into the valence band. I am looking at transitions in the valence band which are of the order of 10 milli electron volts, and this transition is happening in the phonon space, right. So, where so if this has to lose a 10 milli electron energy, right, there is some phonon that has gained this energy, there is some phonon in the material that has gained this energy. Okay. Or it can be the other way around, right. So, if from light I take my material actually so it is also possible that in Raman spectroscopy, so my light frequency is here, right. So, this is energy versus frequency, whereas the detected Raman frequency is somewhere here. So, this is called anti-Stokes peak, which means a phonon has lost its energy, right. So, it has lost its energy and then that energy is taken by the photon, right. So, this is losing of energy by a phonon, right. So, in the phonon energy spectrum, right, there are states where a phonon can be excited to, and that is a real absorption process. Okay. So, such a spectroscopic technique where I shine light, right, of frequency, I shine light of energy E naught and then I measure the same light, okay, of energy E1, and then I say that my material has absorbed E naught minus E1 amount of energy. Okay. Such a spectroscopic technique is what is called absorption spectroscopy. Where I shine light and I measure the same light that comes out, right. So, or I shine photon and I look at how much energy does this photon give away to the material, right. So, this is a classic example. Raman spectroscopy is a classic example of what is called absorption spectroscopy, right. There is also scattering, because with absorption also photon will change its direction, right. So, it will change its momentum. So, you can also measure the momentum of photon, that's Raman scattering, but so you can use it for as an absorption spectroscopy technique, right. So, where you shine light and then you measure the energy of the light that comes out. Okay. So, so you can do so this is the definition of what is called absorption spectroscopy. All right. Now, so up to now let us again summarize 0 to 100 gigahertz is just impedance spectroscopy, right. Then about so let us say, or let us write energy scales, that is better. 0 to so something like 0.1 MeV, right. So, these are the energy scales that I can measure using impedance spectroscopy. Energy scales of excitations, electron excitation, I am always looking at electron excitation, right. Then about 1 MeV to 100 MeV, right. So, I am going to split this up as the Terra-Hertz spectroscopy, the Brillouin spectroscopy, and so if I look at 10 to 100 MeV, that is like Raman spectroscopy. So, where you are actually looking at the phonon modes of the material, right. And Raman spectroscopy, so this is one of the absorption spectroscopy techniques. Okay. So, we sort of classified spectroscopy as absorption, which is also related to scattering, right. So, if I am absorbing I am also scattering, and the third one is what is called emission spectroscopy. We will come to emission spectroscopy very soon, right. So, we will see what that means, but first so you get an idea of what absorption spectroscopy is. So, I shine a photon, right, and then I of h nu, and then I measure the same photon of h some lost energy or gained energy, right, h nu 1 or h nu 2, something like that, right. So, and then this nu minus nu 1 is the lost energy, is absorbed energy. Okay. All right. So, still I am at nano electron volts, right. So, or sorry, I am at milli electron volts. Now, if I look at something like I have again I am looking at bonding electrons. Bonding electrons are somewhere close to the valence band, right. Bonding electrons or bonds, right. So, these are the phenomena that all these things look at, right. So, ionic polarizabilities which are related to the bonds extending and contracting, right, and bonding electrons and corresponding phonon spectrum, right. So, these electrons, if they have to gain energy, they give it off to some phonons, right. So, or if they have to vibrate, right. So, if the bonds have to vibrate, this is equivalent to lattice vibrations, and the energy is taken away by the lattice vibrations or phonons, right. So, there is some, the dynamics is happening even at an electronic scale, because these bonds are vibrating means electrons are vibrating, but we look at it as a phonon, right. So just I mean that, do not confuse, oh here I am talking about electrons, but you are saying phonons. It is just the bonds, right. So, if the bonds are vibrating, that means so your electrons are also oscillating, right. So, every bond is polarizable, and bond is made up of electrons, right. So, the outer shell electrons, the valence electrons, and so that problem I am looking at it as some sort of a sound wave or some sort of lattice vibration or phonons, right. So, it is one and the same, the picture is more or less the same. And in phonon spectrum, I look at the energy levels and I say that okay, so these vibrations can have different vibration energy levels, some of them are real, some of them are virtual, and so if the excitation is to a real state, I have Raman I have absorption. If the excitation is of a phonon is to a virtual state and the phonon comes back, then it's a scattering process, right. So Raman spectroscopy, for example, can look at both absorption and scattering. Okay. All right. So that is so we are at 100 MeV, right. But if I again, so this is conduction band and this is valence band. Typically, so I want to actually look at transitions between valence band and conduction band, right. So, so if I have to look at transitions, interband transitions, these are called. Right. So, electronic processes, so electrons, I am still near the conduction band and valence band of the electrons, but if I look at an atom, right, so and then look at its where are all the electrons, right. So, I have not just valence bands and conduction bands, this is the conduction band, this is the valence band, but I also have what are called core levels, right. So, below the conduction band and valence band, so if I take something like titanium atom, right. So, or let me make my life easier, if I take something like sodium atom, sodium is 1s2, 2s2, 2p6, 3s2, right, and if I 3s1, right. So, if I make a solid out of sodium, then what I have, the band structure will look something like this. I have a 3s band which is half filled, because now I am putting 6.023 times 10 power 23 sodium atoms together, right. If I bring 2 sodium atoms together, the 3s level will split up into 2. Right. So, this is the 3s level of sodium 1, this is the 3s level of sodium 2, right, it will split up into 2. Like that, if I bring 6.023 times 10 power 23, this the band will split up into 6.023 times 10 power 23 different states, and that is a complete band, right. So, that is why I get a band, right. Now, that is okay. So, since 3 s orbitals start overlapping and they come within a bonding distance, I form a band. Okay. Similarly, I also start forming valence band. Valence band is the 2p band. This is completely filled, right. This is half filled, this is completely filled, right. Then I go further deeper, closer to the sodium nucleus. these bands, these orbitals do not even are at an overlapping distance with respect to each other. So, they just belong to one sodium atom, right. So, I will have 6.023, the degeneracy is not lifted. So, I will have 6.023 10 power 23 states of 2s, I will have 6.023 times 10 power 23 states of 1s, right, and then there are all these nuclei of sodium atoms which are spatially separated, right. So, this is spatial coordinate, right. If there is an electron in the 3s state, that electron belongs to the entire sodium solid, right. So, it belongs to all these atoms, right. So, I cannot really pinpoint and then say you came from this atom. No, I cannot say that. I cannot say that this electron came from this atom or this electron came from this atom, not here. But if there is an electron in what is called the core level, these are what are called core levels, then I can pick out an electron and then say this electron actually came from this sodium atom, this electron actually came from this sodium atom. So, these are what are called localized electrons, they are localized to one or one or two sodium atoms, right. Now, if I want to understand the complete material property, I have to understand everything, the dynamics of 3s electrons, dynamics of 2p electrons, dynamics of 2s electrons, dynamics of 1s electrons, right. So far, and this is somewhere here is the vacuum level. So far, so up to 100 MeV we have just understood the processes that are happening in the conduction band and valence band, right. So, the vibration processes, the small intra band transitions and things like that, right. So up to 100 MeV we just probe only up to valence band of the system, or in other words bonding electrons and their dynamics. Right. So, that is what we did until now. Now, let us up the ante, right. So, now what are the standard processes that I would like to know about, right. So, that I may have studied, there is a valence band, there is a conduction band. Okay. So, now I shine light here, if I shine light, so that there should be an excitation of an electron from valence band to conduction band, right. Now, if I shine light, the frequency h nu is greater than the band gap, right. So, this interband excitation can happen. So far the shown energy is much less than the band gap energy, right. So, until 100 MeV, and so there are no interband transitions. Now, since band gap is in the order of of electron volts, right. So, 0.1 to a few electron volts, right. So, 10 electron volts let us say. So, depending on which material you are taking, to excite an electron from valence band to conduction band, I need to use energy scales of the incident photon should be in the range of 0.1 to 10 eV, right. Now, we are going off from milli electron volts to about eV scales, right. Now, what is 0.1 to 10 eV or 0.1 to something like 10 eV, that scans infrared all the way up to UV, yeah, right, frequencies, right. Now, I am talking about 10 power 15 hertz, 10 power 15 hertz, or so I can just 10 power 15 hertz to 10 power I think I can go up to 16 hertz or something like that. So, 10 power 0.1 to 10 eV is about 2 orders of magnitude. So, 10 power 14 to 10 power 16 hertz. Okay. So, this is the range of frequencies that I cover, right. So, 10 power 13, 10 power 14, 10 power 15, 10 power 16 hertz, and these are the typical what are called optical measurements, right. So, I have a source of light which is infrared, right. So, 1550 nanometers, or that is about the low infrareds, right. And it goes all the way up to deep UVs, right. So, where is visible frequency here? 0.1 eV to 10 eV, right. Now, silicon has a band gap of 1.1 eV, right. Now, this is still, if I convert this into energy, so I can just convert this into energy as 1240 divided by 1.1, right. So, into nanometers, sorry. So, this is the wavelength is 1240 nanometers divided by 1.1, right. So, that is that still greater than 1000 nanometers. So, greater than 1000 nanometers is IR. Okay. So, I have IR. So, silicon band gap is in the IR wavelengths. Okay. So, just to give you a feel for some numbers. Now, if I take something like fluorescent materials, cadmium sulphide, right. So, cadmium sulphide has a band gap of around let us say, I do not remember the exact values, but let us say 2.5 electron volts, right, or 2 electron volts, that is easy to calculate, right. So, then what is the wavelength of so the photon that I need to use to excite cadmium sulphide, to excite an electron from valence band to conduction band, right. So, this is Eg, this is conduction band. So, what is the wave this is 1240 divided by 2, that is about 620 nanometers. Now, 620 nanometers, actually this is slightly more than that, 2.2. So, that comes out to be about 540 nanometers, and 540 nanometers is green light, right. So, I can use anything which is I can use blue light to excite this, right, but not red light. Red light will have less greater wave length or lesser wave frequency than 540 nanometers, right. So, I can use green light to excite cadmium sulphide. Okay. So, now I can do these interband processes, right. So, how so how I excite an electron from valence band to conduction band. If there is a real state there, then I am actually going to measure the absorption, right, or imaginary part of epsilon, right. If there is no real state there, if the band gap is 10 electron volts and I give a light, I give green light, there is going to be no real state there, right. So, there is going to be no absorption, but what I end up measuring from the scattering techniques or from the spectroscopic technique is the real part of refractive index, right. So, and so on and so forth. Okay. So, let us look at the optical techniques in the next class and then conclude it by so we are still in the valence band, right. So, we have to still keep going deeper and deeper and try to understand the core level electrons also, right. So, what are going to be the dynamics of that, and then if I know the entire electronic structure, that is really understanding the complete dynamics of my material, right. So, the dynamics of all different types of these electrons, right. So, which happens at different energy scales. Up to valence band 100 MeV is enough. For excitations between valence band and conduction band, I need to go from EV, right. So, a few EVs, right. Then if I have to further go down, I have to up my ante, I have to go up to 10 EVs, 20 EV, 30 EV and so on and so forth, right. So, we will look at these higher energy scales in the next class, but we will start by looking at the optical measurements, optical spectroscopic techniques. Okay. So, let us end here, and I will again meet you in the next class, where we will look at the optical spectroscopic techniques. Again, this time we will specifically classify what is absorption, what is scattering, and what is the emission spectroscopy, or what we call as photoluminescence spectroscopy. Okay. So, we will start there in the next class, and hopefully by next class we should finish the entire course. Okay. All right. So, thank you very much. I will see you again in the next class.